In the preceding clip, we encountered the integral of sine to the fourth theta with respect to theta. And just for a little brush up on integration technique, let's see how this could be integrated. Now, first of all, sine squared theta is 1 minus cosine squared theta. So this being the integral of sine squared theta times sine squared theta d theta, we can write this as the integral of sine squared theta times 1 minus cosine squared theta d theta. And that, if we distribute, gives us the integral of sine squared theta minus d theta minus the integral of sine squared theta cosine squared theta with respect to theta. Now, it's not clear that this is progress, but it's clear that we do know how to integrate sine squared theta with respect to theta. We've just seen that in recent examples. Now let's just consider the integral of cosine squared theta sine squared theta d theta. This can be integrated by parts as follows. Let's let u equal, well, it could be either the sine of theta or the cosine of theta. Let's just let u equal the sine of theta, so that du is cosine theta d theta, and then let dv equal what's left, which is sine theta cosine squared theta d theta. Now, integrating this, and I'm not going to go through the details, but if I did a substitution, let's say w equals cosine theta, then dw would be negative sine theta d theta, and we'd have a w squared over 2 dw, so that v would equal the negative of w cubed over 3. That would be cosine cubed theta over 3. So that using integration by parts, we're going to have uv, which is going to be negative sine theta cosine cubed theta over 3 minus the integral of v du. Now v has a negative on it, so I'm going to go ahead and take care of that by changing the minus to a plus. And now I have u dv and I said that backwards, v du is going to be cosine to the fourth theta over 3. Now, we started with a sine to the fourth theta. We got an integral of sine squared theta d theta, which we know we can do. It's going to be negative 1/2 sine theta cosine theta plus theta over 2, as we've seen earlier. This integral now comes down to a term, an antiderivative term, but then we have an integral of the cosine to the fourth theta. Now, is it any progress to go from a sine to the fourth theta to a cosine to the fourth theta? Well, it turns out that it is. And let's write down where we are in the whole process. We started out with the integral of sine to the fourth theta d theta, and we found that that's equal to the integral of sine squared theta d theta minus the integral cosine squared theta sine theta d theta. And that integral has turned out to be equal to the negative sine times the cube of the cosine over 3 plus the fourth power, the integral of the fourth power of the cosine divided by 3. So being careful to keep the sign straight, we're going to be able to say that this becomes plus sine theta cosine squared theta cosine cubed theta over 3. And then we're going to have minus an integral of cosine to the 4th theta over 4 d theta. Now let's just observe the cosine to the 4th theta is cosine squared theta squared. So this integral is going to become, now let's do this, minus the integral of, okay, and I'm going to jot it down up here, cosine to the 4th theta equals cosine squared theta quantity squared, which is 1 minus sine squared theta quantity squared. And if I square this, what do I get? I get 1 minus 2 sine squared theta plus sine to the 4th theta inside the integral. And of course, that's all divided by, now let's see, hang on a minute. This denominator here was 3, not 4. Our integral of v du is cosine to the 4th theta divided by 3. So let's correct that. Might be halfway unreadable, but I'll try to patch that before we're done. Okay, so in any case, I have a 3 in the denominator here, not the 4 that I wrote down previously. Okay, I went ahead and stopped and patched this. Can't do anything about the fact that this is a really bad looking 3. So I have what? I have the integral of sine to the 4th theta d theta equals, again, an integral we know how to do, sine squared theta d theta, plus just plain old sine theta cosine cubed theta over 3, and then minus this integral. Now notice that this integral includes just the integral of 1/3 with respect to theta, which we can easily do, a 2/3, and if we take the minus of the minus, it is a plus 2/3, the integral of sine squared theta d theta, which is just can be added to the integral of sine squared theta d theta here, giving us 5/3 of the integral sine squared theta d theta, and a negative 1/3 times the integral of sine to the 4th theta over 3. And I think I said a minus 1/3. It's a minus 1/3 integral sine to the 4th theta with respect to theta, which can be added to both sides, giving us a 4/3 sine to the 4th theta d theta over here. So we're going to end up with 4/3 the integral of sine to the 4th theta d theta equals a bunch of stuff over here that we have already integrated, or at least know how to integrate, and then taking 3/4 of the expression we get here and actually doing the integration, we end up with an integral sine to the 4th theta d theta. There are alternative ways to do this, and some of them a little bit more elegant, but what we've done here relies only on the Pythagorean identity, the fact that the sine squared theta is 1 minus cosine squared theta, and the ability to recognize and pursue reduction formula. I don't even guarantee that I've got all the constants right here. You see me make errors of that nature, and I'm not going to double check it. I'm not going to pursue the rest of this integral. I'll leave that as kind of an open question whether I've got everything right, but this is a guide to how the integral can be performed, and it does end up with the result 3 pi over 16. In other words, this integral here, when we back substitute the 1 minus x squared for the u, and evaluate at the limits, we do end up with 3 pi over 16. And I believe our 11 pi over 24 is then at least a plausible result for the mass, and I believe that's correct.